All right, let's dive into a hidden science story that's probably happening in your house like right now. We're talking about hard water. You've heard the term, but what is it really? Why is it such a huge deal for big industries? And what does it actually take to make the water from your taps safe enough to drink? Let's get into it.
So, have you ever been in the shower, right? You're trying to get a really good lather going with a bar of soap and it just fails? It's like you scrub and you scrub, but instead of all those rich, bubbly suds, you just get this weird kind of filmy residue. It is super frustrating, and I'll tell you right now, the problem isn't the soap, it's the water itself.
And this really shows you what's going on. On the left, you've got soft water. It plays nice with soap, you get a great lather, everything's perfect. But on the right, that's hard water. It basically fights the soap, and that's what creates that strange, filmy scum. So, what actually makes water hard in the first place?
Okay, let's play detective for a minute. We're going to uncover the culprits behind this whole mystery. We're taking it from a simple observation in your bathroom right down to the fundamental chemistry that explains all of it.
So the bad guys here are two main ions, calcium and magnesium. It's pretty simple, really. As rainwater soaks into the ground, it flows over rocks like limestone, and it just dissolves these mineral salts along the way. The water picks them up, and boom, those dissolved minerals are what make the water hard. This is also why groundwater is almost always harder than, say, river water, because it spends a lot more time hanging out with these rocks.
But get this, it turns out not all hard water is the same. You've got temporary hardness, which is caused by bicarbonates. You know that crusty white stuff that builds up in your kettle? That's it. And you can get rid of it just by boiling the water. But then there's permanent hardness. This stuff comes from chlorides and sulfates, and boiling, it does absolutely nothing to them. And that's where the real problems start.
And yeah, these problems go way beyond just soap scum. When you're talking about an industrial setting, hard water isn't just an annoyance, it's a massive threat to both efficiency and safety.
So just imagine this is a pipe inside a giant industrial boiler. When you take hard water and heat it under a ton of pressure, all those minerals we talked about, they basically crash out of the solution. They form these little particles that either float around as this loose, slimy gunk called sludge, or, way more dangerously, they bake onto the walls as a hard, rock-like coating called scale. All right, so here's the breakdown. Sludge is soft. It forms in the cooler parts of a boiler, so it's not a huge deal. But scale? Scale is hard. It sticks like glue to the hottest surfaces, and this is the really crucial part. It is a terrible conductor of heat. It's basically like wrapping the inside of your pipes with insulation, and that creates some serious problems.
And here's why that is so bad. If you've got scale coating the inside of a boiler, you have to burn way more fuel just to get the water hot. It's a massive waste of energy and money. Even worse, the metal of the boiler itself starts to overheat, which makes it weaker and can actually lead to a catastrophic explosion. Think of it like clogged arteries for an industrial system. It's inefficient and it's incredibly dangerous.
So, how do we fight back? How do we stop the scale and the sludge? Well, we use some really clever chemistry. Let's take a look at how science has figured out how to solve this whole hard water problem. Okay, this is one of the coolest solutions out there. It's called the ion exchange process. Now, I know the diagram looks a little complex, but the idea behind it is actually pretty simple. You put hard water in one end, and you get incredibly pure, demineralized water out the other. All the magic happens inside those two towers, which are packed with special materials called resins.
Let's break it down. So in that first tower, the resin acts like a super strict bouncer at a club. It sees those troublemaker positive ions, the calcium and magnesium, and just grabs them. It then swaps them out for harmless little hydrogen ions, H+. Then the water flows into the second tower. A different resin in there does the exact same thing, but for the negative ions, like sulfates, and it swaps them for hydroxide ions, OH-. So what's left in the water? Just H+ and OH-. And what happens when you put those two together? You get H2O, pure demineralized water. It's a seriously elegant way to clean things up.
So that's how you get ultra-pure water for something like a factory. But what about the water that comes out of your tap at home? That needs a totally different, but just as important process to make sure it's safe for all of us to drink.
This whole diagram shows you the journey your water takes. It starts at a source, like a river, and then it goes through this whole multi-stage process before it ever gets to your house. And there are really two main goals here: clarification, getting rid of all the visible dirt and gunk, and disinfection, killing any of the nasty germs you can't see.
So step one is called coagulation. Basically, they add some chemicals to the water, and these chemicals make all the tiny floating bits of dirt stick together.
They form these bigger, heavier clumps called floc.
Now that you've got these bigger clumps, the next step is to get them out. The water is passed through huge filter beds made of sand and gravel. It's pretty low-tech, but it works. These filters physically trap all that floc, and the water that comes out the other side is much, much clearer.
And honestly, this is probably the most critical step for our health. Disinfection. A small, very carefully controlled amount of a disinfectant, usually chlorine, is added to the water. This is what kills any dangerous bacteria or viruses that might have made it through the filters, making sure the water is finally safe for us to drink.
Okay, so after all that treating and filtering and disinfecting, how do we actually know the water is safe? Well, that's where official standards come in. They set very clear, very strict limits for what is and what isn't allowed in our drinking water.
And here's where we get to the actual numbers. This table shows a few key metrics from the Bureau of Indian Standards, the BIS. You can see they measure things like turbidity, which is just a fancy word for cloudiness. They also have limits for total hardness and total dissolved solids. But look at that line for E. coli, a huge red flag for contamination. The limit shall not be detectable. That's a zero-tolerance policy right there. These strict standards are the final promise that our water is safe.
So there you have it. From a frustrating shower to massive industrial boilers to the really cool chemistry of purification, the science of water is everywhere. It's this constant, invisible battle against minerals and microbes, all to deliver clean, safe water. Which really only leaves one last question to think about the next time you turn on your tap.